Hi, today we're looking at electric potential in a uniform electric field. So a bit about uniform fields. We can normally only have a uniform electric field if we have two charged plates that are parallel to each other. So it looks something like this, where we'd have one plate that's positively charged, one plate that's negatively charged, and then our electric field all between those two plates should be the exact same in all locations. Now with our uniform electric field, to come up with our potential energy due to a field, we'll start with our basic work formula. So we know our work is force times distance, and then we can utilize our electrostatic force equation, which is our electric field is equal to force over charge, rearranging that to get force on its own. Our electric field times our charge is our force. So we can substitute that back into our work as force times distance. So that gives us our work is equal to our electric field times the charge times the distance. And that equals our potential energy. Now this brings us to potential energy per unit charge. So our symbol for this is V. So as a charge is moved in an electric field, the electric potential may change. This is referred to as a potential difference or voltage. Now, voltage itself is defined as a change in electric potential or change in electric potential per unit charge. Now, it is a scalar quantity, and it is given by V is equal to our change in potential energy over our charge. Now, a little bit about batteries. Batteries are a source of potential difference. We refer to our positive terminal as having a high electric potential, while the negative terminal has a low electric potential. Now, our electrons move from our negative terminal to our positive through whatever our electric circuit is. So, for example, here is an example of a liquid battery. So we have essentially an anode and cathode, which are our terminals which go into our liquid solution. Our electrons travel from our negative terminal through our circuit, powering whatever we have, to our positive. Now with electric fields, we can calculate the electric field between the plates by using a potential difference between the plates and the distance between the plates. So our electric field is equal to our change in our electric potential, or our potential difference, divided by our distance. So we'll look at an example. We're going to calculate the electric field strength between two plates that are 8 centimeters apart with a potential difference of 9 volts. So we have our distance of plates apart and our voltage, and we're solving for our electric field. So we know our electric field is voltage divided by distance, so we can substitute those values in, and we get that our electric field between our plates is 113 volts per meter. Next example, we have an electron as accelerated from rest through a potential difference of 4 times 10 to the 4 volts. We want to know what is the velocity to which the electron is accelerated to. So we know it's starting out with a velocity of 0. We know that our potential difference is 4 times 10 to the 4 volts. We know the mass of an electron is 9.11 times 10 to the negative 31 kilograms. We know the charge of an electron is 1.6 times 10 to the negative 19 coulombs, and we're looking for a final speed. So I would start out with our change in potential energy is equal to our charge times our potential difference. Now, our change in potential energy is also going to equal our change in kinetic energy. Now, because we didn't have a starting kinetic energy, our change in potential energy will just equal our final kinetic energy, so therefore we know it's going to equal 1/2 mv squared. So we can make those two equations equal to each other. And then we want to rearrange and solve for our velocity. So I'd multiply both sides by 2, divide by the mass, and then take the square root of both sides. At this point, substitute our values in, and we get 1.2 times 10 to the 8 meters per second.